Hi, we're going to start our last chapter on electrochem. So, electrochem is just an example, another application of equilibrium. So, we remember from thermodynamics that you can get work out of a system if it's a spontaneous process. And so, any reaction that's not at equilibrium can be used to get work out of a reaction. So we're going to have to remember how to balance redox reactions. So we will practice these. This is the flow chart that you would have used in Chem 107 to balance redox reactions, because electrochem involves the movement of electrons. So if there's a desire for electrons to move in an oxidation process as a product into a reduction process, where the electrons are a reactant, if you set it up right, you can set it up so that the flow of electrons in the redox reaction can be used to do work. So the kinetic energy of the movement of those electrons can be used as useful work. So we will have to go back and practice redox. This is just an example. So an example of a redox reaction. So you have to have something oxidized and something reduced. So the dichromate plus chloride. Chloride is giving up electrons, so we know that's the oxidation. And that means excuse me, I'm going to sneeze. Excuse me, that the chromium must be picking up electrons. So when we balance half reactions, we are going to follow that flow chart. The first step is split it into the two half reactions. So we know chromium has to go to chromium, chlorine has to go to chlorine. Then we're going to balance the elements other than oxygen and hydrogen. So in the first case, the dichromate has two chromiums and the product only has one. So we have to put a red 2 before the chromium on the product side. And then the opposite for the chlorine, you have two chlorines in the chlorine molecule, whereas just one in each chloride. So we have to multiply that by 2. Then we're going to balance the oxygen by adding water to the side that needs oxygen. So if we look back here, you have 7 oxygens on the reactant side. So we're going to need to put 7 water on the product side. And then as soon as you do that, the hydrogen is off balance. So now the oxygens are balanced, the chromium's balanced. We've added 7 hydrogen in the form of water. And so we have to add 14 H plus. So remember, we're adding water and H plus because we have to add things that are in our solution. So this reaction we're balancing in an acidic solution. So we know we have H plus and we have water. So after you do that, whoops, and when you look at the second half reaction, it doesn't need any oxygen or hydrogen, so it's already balanced elementally. But then the other thing we have to do is balance the charge. So in the first reaction, on the right-hand side, we have 2 times 3 plus. That makes it 6 plus. Each water molecule is neutral. Doesn't matter what the charges might be inside. If it adds up to a neutral molecule, it's not charged. On the left-hand side, we have 14 plus and 2 minus, so that means we have 12 plus. So 12 plus has to go to 6 plus, and the only thing you have to balance the charge now are electrons, because if you tried to balance the charge by adding any elements, you'd get the elemental balance off. So we add 6 electrons to the reactant side, and now both sides have a plus 6. In the second one, it's easier to see. You have 2 times -1 on the reactant side, 0 on the product side, so we have to add electrons to the product side. Remember, when you're doing this, if you don't get electrons on each side, so the top reaction ends up being a reduction, where the reactants are gaining electrons, and the second reaction ends up being an oxidation, where something is producing electrons. If you don't come up with that situation, something has to be wrong, because you have to have an oxidation and a reduction together in order for the reaction overall just to be an exchange of electrons. So we need to have the electron number equal. So you need to have enough reactants and products so that the number of electrons gained in the reduction is equal to the number of electrons lost in the oxidation. If you didn't have that balance, then you'd either be pulling electrons from outer space, or you'd be putting electrons into outer space, and that's just not going to happen. So we're going to balance or multiply the second reaction, the oxidation, by 3, which will give us 6 electrons as a product, because we need to balance that with the 6 electrons as a reactant in the reduction process. So once you do that, you're going to add it up. You're going to balance things that are the same on each side. So we can cancel the 6 electrons, and we're left with that balanced reaction. Your last step should always be to check to make sure it's balanced. If the elements are balanced, reactants to products, and if the charges are the same overall on reactant side and product side, you pretty much can be confident that you balanced it right. So electrochemistry, which we're going to use these redox reactions for, it's the area of chemistry concerned with the interconversion of chemical and electrical energy. So if a chemical reaction wants to take place, if you can harness some of that desire for electrons to move from the species that's being oxidized to the species that's being reduced, then you can harness that as electrical energy. So we call a cell that's taking advantage of a spontaneous reaction and it generates electricity a galvanic or voltaic cell. So if we know a reaction is going to go a certain way to reach equilibrium, then we know that that's the galvanic cell we want to set up. We want to set it up with the chemistry such that the reaction isn't at equilibrium and it will go towards equilibrium, and I can harness that energy of that spontaneous process. Electrolytic cell is the opposite. It's where you're plugging something into the wall. You're using that electricity to drive a reaction that's not spontaneous. And we talked about that in thermodynamics, that if a reaction isn't spontaneous, it's the same thing as saying you'd have to put work in. And in this case, when it's electrical energy you need, all you have to do is plug it into the wall where we have electricity. Electricity is simply movement of electrons, and that movement creates kinetic energy, and you can harness that energy. So here's an example of a galvanic cell. Zinc solid plus copper 2 plus. The electrons are exchanged in an oxidation and a reduction process so that you get zinc 2 plus and copper solid. This just shows you a picture of that, and I'll do a demo in class showing you one of these processes. So when it's set up like this, you can't get any electricity out of it because the oxidizing and reducing agents, the copper 2 plus and the zinc solid, are in the same flask. So they are just going to randomly exchange their electrons. If you set it up differently, so if we set it up so that what's being oxidized and what's being reduced are separated from each other, then the only way for those electrons to move in this picture are through this wire. So they're going to move from one side to the other. And we saw that they are moving. Oops. So that copper is becoming a solid. So you're having electrons going from the zinc side over to the copper side. So then the other half reaction takes place over there. The big pieces of metal that carry the electrons into and out of the solutions, those are called electrodes. And the side where you have reduction is called the cathode. The side where you have the oxidation is called the anode. So the electrons are moving, their kinetic energy is being used to light this light bulb. The other thing that you have to remember is that as the electrons move from right to left, you're building up charge, negative charge on the left-hand side and positive charge on the right-hand side. So you won't do that very long because pulling apart negative and positive charges just don't really happen for very long. Everything in your world is pretty neutrally charged because plus and minus likes to be next to each other. So if you put in this salt bridge, if sodium cations flow into the side where the electrons are going, you're going to neutralize the negative charge on the electron with the positive charge on the cation, sodium plus, and then the opposite on the other side. If you're pulling electrons out of the zinc side, then you're going to have to put negative charge back in. So in this case, they're using sulfate. So what you put in a salt bridge, you want it to move fast. so that you don't slow down the process. So you want the ions to quickly move to balance the charge, but they also have to be ions that don't take part in the redox reaction. So at this point, all I would ask you to put is cations and anions, because at this point you probably aren't familiar enough with what reacts with what in order to make a decision, like in this case, that sulfate won't interfere with the redox reaction, nor will sodium cations. So the anode, as I said, is the electrode where oxidation occurs. This is the electrode where electrons are produced. Is what anions migrate towards, and it has a negative sign. So in a galvanic cell, the cathode is the electrode where reduction takes place, the electrode where electrons are consumed. So we know that in the reduction process, electrons are being used up as a reactant. It's what cations migrate towards, and it has a positive sign. So why do negative ions move towards the negative electrode? So let's think about it. So electrons are leaving. This is the, what was it? Yeah, zinc is giving up electrons, right? Yeah, zinc is giving up electrons. So you're going to have zinc 2+ going into the solution. Therefore, you're building up a negative charge as those electrons are leaving that electrode. So in a galvanic cell, this is just showing you that you're going to add up and get the overall reaction, balance the electrons as we did. And then the overall reaction has to be going towards equilibrium. So it must be true that zinc solid likes to react with copper 2+ at whatever concentration you have the copper 2+ to form zinc 2+ or copper. If the reverse reaction happened, you'd have to force that with electricity. So in this case, you're choosing a spontaneous reaction, and you'll call it a galvanic cell. So it gets a little cumbersome to be writing these reactions out all the time. So we're going to use a shorthand notation. The shorthand notation is that the anode goes on the left, the salt bridge is in the middle, and the cathode is on the right. And so essentially you can think of it when you go to translate it into a reaction, the zinc on the anode side becomes zinc 2+, and then the copper 2+ is becoming copper solid. So the chemistry really just flows if you write it in this direction. Each vertical line is a phase boundary. So it's a boundary when you look back here, where you have copper as a solid and then copper 2+ in solution. So that's a difference in phase. Same thing on the zinc side. You have zinc solid and zinc 2+. And then really with a salt bridge, you have two phase boundaries. So you have the phase boundary of the salt bridge going in on one side and on the other side. So each of those vertical lines is a phase boundary, and technically a salt bridge is two phase boundaries where the salt bridge enters each of the solutions. So when we have this cell set up, we have a cell potential, and the free energy changes for the cell reaction we know have to be related to the cell potential. So the cell potential, the electromotive force, is the force or electrical potential that pushes the negatively charged electrons away from the anion and pulls them towards the cathode. So this is that desire for electrons to move. It's also called the cell potential or the cell voltage, and it has units of volts. So if it's very similar to thinking about using water to make electricity. So if I take water to the top of Pikes Peak and I'm going to let it run down and turn a turbine and make electricity, when I take it to the top of Pikes Peak, there's a desire for it to move downhill, but until it actually moves, I don't get any work out of it. So the volts is that tendency, that desire for electrons to move from one side to the other. And then once some electricity flows, and we'll use that unit of a coulomb, the electrical charge that actually flows from one side to the other, then we can get work out of it. And work will have units of joules. So coulombs times volts. So the desire for the electrons to move is the volts the coulomb is the number of electrons that move, and when you multiply those two, you get the energy or the joules of electricity that would have moved. These D's in here should be deltas. So it should be clear to you that if you're using a reaction that's not at equilibrium in order to get work out of it, it's a spontaneous process, that somehow the cell potential must be related to the delta G. So these capital D's should be deltas. So delta G equals negative NFE. So number of electrons that moved is the N. F is Faraday's constant, which just converts between the unit of charge of electricity from a coulomb to how many moles of electrons that would be, and then the cell potential. So you could do that if you're not in standard state, or you could say the same thing, that delta G standard state would be equal to negative number of moles of electrons, Faraday's constant, times the standard state cell potential. So the cell potential when all gases are at 1 atmosphere and all solutions have a concentration of 1 molar. So this is just showing you how you'd use that equation. So the standard cell potential is 1.1 for this reaction. Calculate the standard free energy change for this reaction. So the cell potential goes here, the 1.1 volts. And the 2 comes from the fact that as you've balanced the reaction, that's how many electrons are flowing. So when zinc solid and copper 2+ react, it's a 2 mole of electron process. So 2 moles is N. Faraday's constant is 96,500 coulombs per mole of electrons, multiplied by the cell potential in volts. And then this is just showing you how the units work out. They're converting the joules, which would be from the coulombs times volts, into kilojoules. So the delta G standard state would be negative 212 kilojoules. So how did we get a standard reduction potential? So we want to think about the 2 processes. So if we have this process where the overall reaction is hydrogen gas reacting with copper 2+, making it into the protons, H+, and copper solid, then I want to pull that apart, get my half reactions. The top one, we see the hydrogen is being oxidized and the copper is being reduced. So when I go to my table, they're called standard reduction potentials in my table. So that means that I take it right out of the table for the copper, but what I take out of the table for the hydrogen, I have to reverse the sign. So I would have to take out the cell potential for hydrogen plus going to H2, but then I know in my spontaneous or galvanic cell, this is going to be the anode, so I have to change the sign. Okay, so the hydrogen electrode has been defined to be 0. You can't really measure the individual potentials for one side of a cell. It's always something relative to something else. Where do electrons want to move when 2 things are side by side? So by definition, it's been defined that this H2 gas going to 2H plus 2 electrons, we'll call that 0. And then when I measure the cell potential of that relative to anything else, I will consider that the cell potential of the other half of the reaction. So if this is 0, when I'm measuring 0.34 volts, I will contribute that to the copper 2+ plus 2 electrons. So the standard hydrogen electrode has been chosen to be the reference. So either way it's going, doesn't matter. We would say that that cell potential is 0. So this is just showing you where they came up with the 0.34. So that means out of the table, you're going to get 0 for the hydrogen side. You're going to get 0.34 for the copper side. When you add those 2 together, you end up with the overall cell potential. So in this case, it's positive 0.34. If it's positive, that means this overall reaction wants to take place in the direction you've written it, if everything's in its standard conditions. So if copper 2+ is in 1 molar solution and the hydrogen gas is 1 atmosphere and the hydrogen's in 1 molar, then there's a plus 0.34 voltage for the cell potential. Therefore, this reaction at those conditions is spontaneous. So this is just showing you it could be relative to anything. You always call the hydrogen 0. Now this is calculating another cell potential, and this is whether or not zinc solid could be oxidized by the H plus, and shows a negative cell potential. So under standard conditions of 1 atm and 1 molar for the solutions, that means this reaction isn't spontaneous, so you could not use this reaction in a galvanic cell. This is just a list of some of the cell potential values. So in the back of your book, you have much more extensive table than this one, but it's just showing you where hydrogen is in the middle. And if these are all reduction potentials, that means at the top, these are the things that want to be reduced the most. And as you get towards the bottom, it's the opposite. The oxidation process is favored. So this is just getting these out of the table, and we will practice this. I don't think there's anything else to say because we just did 2 of these with the copper and the zinc. Except to think about this. I mean, I think this is important, sorry. So when you look in the table, you will find, is silver in here? Yeah, silver right here. Silver plus an electron goes to silver solid. The potential for that reduction is 0.8. So notice when you add them, the cell potential you add is 0.8, even though you had to multiply that half reaction to get it to add to the copper with the right number of electrons. And so cell potentials are intensive properties, so they're independent of how much. You want to think of them as they're a tendency for something to happen. So you don't worry about how you've multiplied the reaction. There's a tendency for silver to pick up electrons to form silver solid when it's next to copper solid, which has a tendency to give up electrons in that situation. So even though we multiplied the silver half reaction by 2, we do not multiply the cell potential by 2. So we know that in order to determine if a reaction is spontaneous, we need to know not the delta G naught, but we need to know delta G. So we need to know the Gibbs free energy change for the system that we've set up. And we often don't set up systems with 1 atm of pressure and 1 molar for all the concentrations. So we're going to go back to the thermodynamic chapter and look at how delta G relates to our mixture, and it relates based on the Q. Remember, Q is the same thing as how you'd set up an equilibrium expression, except it's not the concentrations and pressures at equilibrium. So when we look at the top equation and now compare it to what we know is true from this chapter, delta G is also related to cell potential. We can combine those 2 equations to come up with what's called the Nernst equation, that says the cell potential at any particular set of concentrations and pressures is related to the cell potential for standard state minus RT over NF ln of Q. So we've just combined the top 2 equations into this. I would strongly advise there's no reason to use these next 2 equations. You're free to use them. The one right below the Nernst equation has just changed natural log to log, and you do that by multiplying by 2.303. I don't really see any value in doing that. Your calculator can do natural log just fine. And the very bottom one not only changes natural log to log, but it also takes into account that you're going to use an R of 8.314 and that the temperature is 25. It's one of the reasons why I don't like this, because you have to remember that you only use that for 25. So I highly suggest that when you think about the Nernst equation, choose the first form of it and don't worry about these other 2. You're free to use them if you want, but just remember when they apply. So I think I'm going to take a break there, and we'll come back and finish this last half of the chapter, which will be the rest of the material for the class.